This is a continuation of the Chapter 3 problem session, where we are working on problems related to stoichiometry. Question number 13 on page 144. Aluminum metal reacts with oxygen gas to form aluminum oxide. We're given the amount of aluminum, the amount of oxygen, and how much aluminum oxide. What is the percent yield? Well, as you look at this problem, this is a reaction stoichiometry problem. And what is the first thing you need in order to solve any reaction stoichiometry problem? The first thing you need is a balanced equation. We're not given a balanced equation, but we are given a description of the reaction. So we have to use this to write a balanced equation. So aluminum metal. So we ask, what is the formula for aluminum metal? Aluminum metal is the neutral form of aluminum. So Al, solid, that's the aluminum metal. It reacts with, so reacts with, we put a plus. Aluminum metal reacts with oxygen gas. Oxygen gas is one of the diatomic molecules that you need to know. So we'll put O2 gas. You have to have O2. That's the formula for oxygen gas, which you're supposed to know. To form, and when you see to form, you put the reaction arrow, and then over here on the product side, aluminum oxide. Now we have to have the correct formula for aluminum oxide. Aluminum oxide is an ionic compound. The aluminum cation has a 3+ charge, and the oxide anion, which is in group 16, or in the old group 6, has a 2- charge. And when we do the crisscross here to find the formula for the aluminum oxide, we see that it is Al2O3. That's a solid at room temperature, an ionic compound, which is a solid. Okay, so next we need to balance this equation. Now, as I look at this, I'm saving, I don't focus on this side because I can put any coefficient here that I need to. Instead, focus on this side, and I see that there's an odd number of oxygens. And if there's an odd number of oxygens here, but an even number here, I need to make this even. So I'm going to put a coefficient of 2 in front of this. That gives me 6 oxygens, and then I need a coefficient of 3 here. That balances the oxygens. 3 times 2 is 6, 2 times 3 is 6. Now I need to balance the aluminum. 2 times 2 is 4. There are 4 aluminums. So 4 aluminums on the reactant side, 4 aluminums on the product side, and we have it balanced. In a problem like this where you have a lot of data, you'll find it very helpful to write underneath each substance what you're given. You have 2.5 grams of aluminum. So right here I'll write 2.5 grams of aluminum. It reacts with 2.5 grams of oxygen. So the mass of oxygen that reacts is, or that's present is 2.5 grams. It will produce 3.5 grams of aluminum oxide. 3.5 grams of aluminum oxide. Now, as we look at this, this says, what is the percent yield of this of aluminum oxide? Now, over here I'm going to write to the side, I'm going to remind you of our definition of percent yield. The percent yield is equal to the actual yield divided by the theoretical yield times 100%. The percent yield is the actual yield divided by the theoretical yield times 100%. And as I look on the product side here, we are told that we get 3.5 grams of aluminum oxide. So what is that? That is the actual yield. And one way that you can verify that is to insert the word actually in here. If 2.5 grams of aluminum reacts with 2.5 grams of oxygen to actually produce 3.5 grams of aluminum oxide. Yeah, that's what that means. This is the actual yield. So we're given the actual yield. That's how much we actually got. Okay, in order to calculate the theoretical yield, we have to look at our reactants. And this is a case where we have 2 different quantities given. And this is then a limiting reactant problem. In a limiting reactant problem, one of these reactants will be completely consumed, and there'll be excess of another reactant. So we have to determine which is the limiting reactant. You have to do this anytime you see the amounts of 2 substances given. So we can set up 2 cases in order to solve this. The first case is if the aluminum is the limiting reactant. If the aluminum is the limiting reactant, then how much aluminum oxide could we form? If aluminum is the limiting reactant, how much aluminum oxide could we form? So what we'll do is we'll use the technique that we've followed. Now we're going to ignore this 3.5, and for right now we're going to ignore the 2.5. We are assuming that we have all the oxygen we need and that aluminum limits us. So I'm going to calculate what is the maximum number of grams of Al2 2.003 that we could get if we're limited by the aluminum. So I'm going to start with 2.5 grams of aluminum. Now, as always, we convert from grams to moles using the molar mass. So we go to the periodic table, and the molar mass of aluminum on the periodic table is right down here. It's 26.98. So there's 26.98 grams of aluminum per 1 mole of aluminum. Okay, so if you just focus on the units, that carries over. Don't just write grams here. Write grams of aluminum. In a stoichiometry problem, it helps you to know that you're canceling it correctly. So grams of aluminum cancels grams of aluminum. Now we have it in moles of aluminum. We don't want it in moles of aluminum. We want it in grams of aluminum oxide. So I'm going to say times, draw a line, and put moles of aluminum in the denominator. Now this is where we wake up screaming mole to mole ratio. From the balanced equation, I want to know how many moles of aluminum oxide I will get. Moles, Al2O3. How many moles of aluminum oxide can I get from this much aluminum? And so the mole to mole ratio, what is the mole to mole ratio going to be? Well, you get 2 moles of aluminum oxide for every 4 moles of aluminum. 2 moles of aluminum oxide for every 4 moles of aluminum. And that's the correct mole to mole ratio. Now, moles of aluminum cancels, and I have it in moles of aluminum oxide. But I need grams of aluminum oxide. How do I go from moles of aluminum oxide to grams of aluminum oxide? I use the molar mass. So we use the periodic table. And here's where I would just use my calculator. I wouldn't write this down. And I would say 2 times 26.98 plus 3 times 16, and then hit the equals. And when you do that, you'll see that it's 102.0 grams of Al2O3 per every 1 mole. That's the molar mass of aluminum oxide. Now, everything in the numerator we multiply, everything in the denominator we divide, we ignore the ones. Be sure you calculate this out so that you're getting the correct answer. I'm limited to 2 significant figures, so to 2 significant figures I get 4.7 grams of Al2O3. That's the most aluminum oxide that you could get if aluminum limits us. But we have to consider the other possibility. We have to consider the possibility that oxygen is the limiting reactant. So I'm going to write the second case. If oxygen is, and I like to abbreviate limiting reactant. If oxygen is the limiting reactant, let's calculate the maximum number of grams of Al2O3 that we can get if oxygen is what limits us. Now, in this case, we are assuming we have all the aluminum that we need. We have excess aluminum, and oxygen is what limits us. So we will start with 2.5 grams of oxygen. And we will convert from grams of oxygen to moles of oxygen. Now, what is the molar mass of oxygen gas? And here's where you have to be careful. Remember, there's 2 oxygens. There are 2 oxygens per molecule. And so the molar mass is not 16. The molar mass is 32. 32.00 to 4 significant figures. So that gets it into moles of oxygen. But I'm trying to find the grams of aluminum oxide. So I don't want it in moles of oxygen. I will say times, draw a line, put moles of oxygen in the denominator. And I'm going to go from moles of oxygen to what? Well, I'm converting to aluminum oxide, so I will go to moles of aluminum oxide. Now, what is the mole to mole ratio? Well, I get the mole to mole ratio from the coefficients in the balanced equation. So that in the balanced equation, the coefficients are there's 2 moles of Al2O3 per every 3 moles of O2. If you don't get the mole to mole ratio correct, you will not get the correct answer. So the mole to mole ratio is 2 moles of aluminum oxide per every 3 moles of oxygen. And then we'll say times, draw a line. So grams of oxygen cancels, moles of oxygen cancels. I have it in moles of Al2O3. I don't want it in moles of Al2O3. I want it, and this is why I always write down what I want to know, I want it in grams of Al2O3. So how do I go from moles back to grams? It's with the molar mass. It's the same molar mass we had up here, 102.0 grams of aluminum oxide per mole of aluminum oxide. And when we calculate that out and we limit it to 2 significant figures, we will get 5.3 grams of aluminum oxide. So which of those would we get? Well, we would get the smaller amount, because as soon as you have 4.7 grams of aluminum oxide, all of the aluminum is gone, and you can't make any more. You have excess oxygen in this case. So here's what we found out. We found out that aluminum is the limiting reactant and that oxygen is the excess reactant. We like to abbreviate that just with the letters X and S. This is the excess. That means we have more oxygen than we need. Aluminum is what limits us. And that means that this value, the value that we determined, is the theoretical yield. This is what we calculate theoretically we should get if we react this much aluminum with this much oxygen. Theoretically, we should get this. But we actually got 3.5 grams. So now we can finish the percent yield calculation, because the question is asking what is the percent yield of aluminum oxide. And the percent yield is the actual yield, 3.5 grams, divided by what we theoretically should have been able to get, 4.7 grams, times 100%. And the percent yield calculates out to be 74%. In other words, when we mixed this much aluminum and this much oxygen, we got 74% of the aluminum oxide that theoretically we should have gotten, or that theoretically we would have expected to get. So that is the answer, 74%. Question number 14. What is the concentration of a solution formed by dissolving 10 grams of sodium chloride in enough water to form 100 milliliters of solution? Now, the way that we express concentration is with molarity. And you need to know what molarity is. We use a capital block M for molarity. The molarity is equal to the number of moles of a substance, of the solute, divided by the volume of the solution in liters, divided by the volume of the solution. I'll put that as a subscript. It's, for some reason in chemistry we do everything as a subscript, in liters. Now there's a shorthand way to write this. We can say that the molarity is equal to N, which stands for number of moles, over V for volume. There's three terms here. Now, you can always solve a molarity problem as a plug and chug. Sometimes it's easier to do it as a dimensional analysis, but if you get stuck, you can always write this formula and figure out what you're given. So when this says what is the concentration, it's asking for the molarity. Now, so that's what I want to determine. Now this, I'm given the grams of sodium chloride. This is the solute. I need to know the number of moles. So one thing that I want to calculate is the molar mass of sodium chloride. Now we have a lot of M's in chemistry. The capital block M stands for molarity. Capital script M stands for molar mass. This is the molar mass of sodium chloride. And from the using the periodic table, sodium has a molar mass of 23 and 22.99, and chlorine has a molar mass of 35.45. Now I would do this in my calculator rather than writing it down, but I'm writing it down so you can see where it's coming from. I have 22.99 plus 35.45. And so the molar mass of sodium chloride is 58.44. And the units of molar mass are grams per mole. The molar mass of sodium chloride is 58.44 grams per mole. Now, to find the concentration, I'm going to solve this like a plug and chug. I'm going to write the equation then as molarity is equal to the number of moles of sodium chloride in the numerator divided by the volume of the solution in liters in the denominator. Now, I'm not given the moles of sodium chloride, I'm given the mass. How do I go from mass to moles? I do it with the molar mass. And do I multiply or divide to go from grams to moles? I divide. That's what we've been doing all along. So I'm going to take the mass of sodium chloride in the numerator. I'll have 10.0 grams of sodium chloride divided by the molar mass, 58.44 grams per mole. So the units of grams cancels, and this ends up being in units of moles. I'll do all this in my calculator at the end. What is the volume of the solution? Well, you dissolve this much sodium chloride in enough water to form 100 milliliters of solution. Now I've got to express it in liters. Molarity is moles per liter. So how do you convert this to liters? Be sure that you can easily go from milliliters to liters and liters back to milliliters. And in order to do that, you just move the decimal place 3 places to the left. So it's 0.1000 liters. Okay? So in my numerator I have moles, in the denominator I have liters. And when you calculate this out, you get 1.71 moles of NaCl per liter. Now, another way to say moles of sodium chloride per liter is to say, and this is how we would normally express it in chemistry, 1.71 molar, so capital M, sodium chloride. So this is how you express the concentration. When you see capital M, you think moles per liter. It's 1.71 moles per liter of sodium chloride. Okay, so that's the answer to number 14. Okay, question number 15. Suppose that 2.5 grams of sodium chloride are required for a certain reaction. If sodium chloride is available as a 0.150 molar solution, how many milliliters of this solution must be used? Okay, so to do this, let's just do this as a plug and chug problem. The definition of molarity is the number of moles divided by the volume. So that if this is asking how many milliliters, that's the volume. I'm going to rearrange. Volume is equal to the number of moles divided by molarity. So I multiplied both sides by volume. I divided both sides by molarity. So in this case, the number of moles, I need to know the number of moles of sodium chloride. Well, I'm not given the number of moles, I'm given the mass. How do I go from grams to moles? I do the same way I did back here. Mass divided by the molar mass gives me the number of moles. And so the number of moles is going to be 2.50 grams divided by the molar mass, 58.44 grams per mole, divided by the molarity. Now here's 0.150, and here's a suggestion I would have. When you're doing a calculation and you see the unit capital M, you can always replace capital M with moles per liter. When I see capital M, I think moles per liter. And you'll see that the units of grams cancels and the units of moles cancels. This ends up being in units of liters. And so when you calculate this out, you'll get 0.285 liters of solution. Now notice how the question is worded. This says how many milliliters must be used. So how many milliliters would that be? So to go from liters to milliliters, I'm going to move the decimal places back 3 places. This is going to be 285 milliliters of solution. So here's the point. If this is the concentration, 0.150 moles per liter, if I have 285 milliliters, that is equivalent to, or that contains 2.5 grams of sodium chloride. Okay. And question number 16. What mass of solute is contained in 155 milliliters of 0.125 molar sodium sulfate? Now, one of the first things we have to do, we have to make sure we get sodium sulfate correct. So you need to know the formula for sodium sulfate. So be sure that you know the polyatomic ions and the monatomic ions that we covered in Chapter 2. So sodium is in group 1 of the periodic table. It's right here. And so the sodium cation has a +1 charge. And so this is sodium cation. Sulfate is one you just have to memorize. Sulfate is SO4 2 minus. It's not enough to know that sulfate is SO4. You have to know that sulfate is SO4 2 minus. So the formula of sodium sulfate is Na2SO4. In order for this to be electrically neutral, I need 2 sodiums, 2 positive charges for every 2 negative charges. That's the formula of sodium sulfate. Now once I have that, this is sodium sulfate. This says what mass of solute is contained in this much. Now here's the definition for molarity. Molarity is the number of moles per liter. It's the moles of solute per liter of solution. Molarity is N over V. Notice that we're given the volume, 155 milliliters. We're given the molarity. We're not given the number of moles. So we can rearrange and solve for the number of moles. The number of moles is equal to molarity times volume. Now the molarity is 1.25, and anytime I see capital M, I think moles per liter, and I can even write it as moles per liter, and write it as a horizontal line so you can keep track of units. 1.25 moles per liter. This is equivalent to saying 1.25 capital M molar, 1.25 moles per liter. Now I'm going to multiply it times the volume. Now the volume is given in milliliters, but molarity is in moles per liter. I need to convert the volume to liters. So what is 155 milliliters expressed in liters? It would be 0.155 liters. And 0.155 liters, that calculates out to be 0.19375 moles. Now there's only 3 significant figures. I keep the additional significant figures to avoid round-off error. Okay, so that's how many moles of solute I have. And what is the solute? It's sodium sulfate. Sodium sulfate is the solute, Na2SO4. So this says what mass? I want to know the number of grams. So the next step, the number of grams of Na2SO4 is equal to, and I'll start with the number of moles, 0.19375 moles of Na2SO4. And how do you go from moles to grams? It's with molar mass. So I say times, draw a line, I'll put moles of Na2SO4. And the molar mass, I get this from the periodic table. What I would do, I would use only my calculator to determine this. In my calculator, I would enter 2 times 22.99 plus 32.06 plus 4 times 16 equals. You don't have to use parentheses or anything. Your calculator knows the hierarchy of operations. And when you do that, you'll get the molar mass of sodium sulfate is 142.0 grams of sodium sulfate per 1 mole of sodium sulfate. That's grams per mole. And so this calculates out to be 27.5 grams of sodium sulfate. 27.5 grams of sodium sulfate. Okay, very good. Let's look at number 17. This says, number 17 says, what is the final concentration if this volume of hydrochloric acid having this concentration, so I have a volume, this is a volume term, this is the concentration term, I can put this molarity. What is the final concentration? So I'm looking for another concentration. And we're going to dilute it to this volume. So look at this. The 12.5, this is the original volume, and the 12.0 moles per liter, that's the original concentration. The final concentration is M2. And the final volume, we dilute 12.5 milliliters to 250 milliliters. We add water until we have a total of 250. This is the final volume. So this is a solution by dilution equation. Solution by dilution. If you take a concentrated solution and if you dilute it, you can calculate the new molarity using this formula. M1V1 equals M2V2. So that's an equation that you need to know. So it's called the solution by dilution equation. Now notice that in this case we want to know what the final concentration is, so we need to solve for M2. So we're going to see that M2 is equal to M1V1 over V2. Now my suggestion is before you plug the numbers in, first rearrange the variables and then plug the numbers in. You're less likely to make a mistake. So what is the original molarity? It's 12.0 capital M molar. What's the original volume? It's 12.5 milliliters. Now notice I did not convert this to liters, and that's okay. In a solution by dilution equation, you can use any unit for volume as long as you're consistent, as long as both units of volume are the same. So I'm going to leave this in milliliters. I'll divide by the new volume, and the new volume is 250 milliliters. I should have a decimal point here to emphasize that that has 3 significant figures. Okay. The units of milliliters cancel, and we end up in units of molarity. And this calculates out to be 0.6 molar HCl. So look what happened. We took concentrated hydrochloric acid with a concentration of 12.0 moles per liter. We added water. That diluted it down to a lower concentration, 0.6 moles per liter. Okay, so we've been working with molarity, and we need to see how to do a solution stoichiometry problem. How to do a solution stoichiometry problem. Now, the one kind of problem that we've covered in Chapter 3, the one kind of reaction that you need to know, is a reaction involving acids and bases. This would be an acid-base titration. So in an acid-base titration, this sodium hydroxide is a base. This is a base. And hydrochloric acid is an acid. And you see this word to neutralize. So what we need is a balanced equation. So you need to write the balanced equation that occurs here. And the balanced equation, I'm going to write the formula for the acid. It's HCl aqueous. Reacts with the base, sodium hydroxide, aqueous. Now in class, I emphasize that in any acid-base problem like this, an acid will react with a base to form a salt plus water, and they swap ionic partners, so that the cation, H+, combines with the anion, OH- to form water. The sodium cation combines with the chloride to form sodium chloride. Now, that means there's a little bit of a shortcut here. For every H+, there has to be an OH-, and that tells you that the mole-to-mole ratio must be 1 to 1. It must be 1 mole of HCl per 1 mole of NaOH. Now, if you don't see that, let's go ahead and write the balanced equation. And in an acid-base neutralization reaction, you have an acid reacts with a base to form a salt. Now, we just swap ionic partners. You have to know your ions. The cation over here is sodium cation. The anion is chloride. So NaCl, that's still dissolved in the water, so that's aqueous. A salt plus, and if we're swapping ionic partners, we're going to combine the H+ with the OH- and get water. Now, I'm going to write water a weird way. I'm going to write water, HOH. Now, that's not the normal way to write water, but I'm writing it this way to emphasize that in an acid-base reaction, every H+ combines with an OH- to form water. So that's what we see. And you can see now that it is balanced. There's one H+, one OH-, so one water. There's one sodium cation, one chloride, so one sodium chloride. Now, one thing that I like to do when there's lots of data here, say I've got three numbers, 1.5 molar, 46.3, 1.25. What I like to do is underneath the equation, I like to write the quantities that are given and what we're looking for. So this says how many milliliters of sodium hydroxide. So I want to know the number of milliliters. I put milliliters concentrated, but question mark, but the concentration is 1.50 molar. So that's what I know about sodium hydroxide. Now, for the hydrochloric acid, you have 46.3 milliliters, and the concentration is 1.25 molar of the acid. So I've combined everything. Now, there is a shortcut that we can use for this problem. Okay. And here's the shortcut. Now, you've got to be careful about this. Since the mole-to-mole ratio of acid to base is 1 to 1, since the mole-to-mole ratio of acid to base is 1 to 1, then that means that the number of moles of HCl must equal the number of moles of sodium hydroxide when this completely reacts. At the neutralization point, that is at the point that this acid is completely neutralized, at the neutralization point, the number of moles, remember the little n stands for number of moles, of the acid is equal to the number of moles of the base. Because it's a 1 to 1 mole-to-mole ratio. Now remember what molarity is. Okay? Molarity is the number of moles over the volume. We have molarity and volume here. We have molarity and we're looking for the volume here. I can rearrange and solve number of moles is equal to molarity times volume. Okay, so let's go over here and complete this. So if this is true, I'll rewrite this. At the neutralization point, the number of moles of acid equals the number of moles of base. Well, look at this expression. What are the number of moles of acid? The number of moles of acid is the molarity of the acid times the volume of the acid. What's the number of moles of base? It's the molarity of the base times the volume of the base. This is the same as the solution by dilution equation that we used on the previous problem. M1V1 equals M2V2. Now, you can only use this if the mole-to-mole ratio is 1 to 1. But the mole-to-mole ratio here is 1 to 1. And it asks how many milliliters of base. So I'm looking for the volume of the base. So I'm going to rearrange and solve for the volume of the base. The volume of the base. Now, my suggestion is before you plug the numbers in a plug and chug, rearrange the variables first. You're much less likely to make a mistake. The volume of the base is the molarity of the acid times the volume of the acid over the molarity of the base. So I just divide both sides by the molarity of the base. Now I plug in the molarity of the acid. HCl is the acid. The molarity is 1.25 molar. The volume of the acid is 46.3 milliliters. Remember, in this kind of equation, as long as we're consistent, I can use any unit for volume I want to, so I'm going to leave this in milliliters. Divided by the molarity of the base. What's the molarity of the base? 1.50 molar. You can see that the units of molarity cancel. I end up in units of milliliters, and the volume of the base calculates out to be 38.6 milliliters. It takes 38.6 milliliters of base to completely neutralize the 46.3 milliliters of the acid. And we can use this shortcut. Okay? But I've got to emphasize this. Let's go back up here. I'm going to say, be careful. Danger, Will Robinson. Be careful. This shortcut only works if the mole-to-mole ratio is 1 to 1. Let's underline that to separate that from the word base. This shortcut only works if the mole-to-mole ratio is 1 to 1. So let's look at an example where the mole-to-mole ratio is not 1 to 1, and that's question number 19. Okay. And in number 19, what volume of barium hydroxide is required to completely neutralize this much nitric acid? What's the first thing we need? We need a balanced equation. So nitric acid is HNO3. HNO3. That's the acid. That's nitric acid. And it reacts with barium hydroxide. Okay, so what do you have to know about barium hydroxide? Let's go to the periodic table. Barium is in group 2 of the periodic table. It has a +2 charge. Hydroxide is OH minus 1. You have to know then the formula for barium hydroxide is Ba parentheses OH2. Now, as our shortcut, remember in balancing this, if you're running out of time, the shortcut is for every H plus, there must be an OH minus, because that's what's driving these reactions. So how must I balance this? Well, if you followed what I've said, for every H plus, there must be an OH minus. I need 2 moles of nitric acid per every 1 mole of barium hydroxide. Now, that's the shortcut. If you don't see why it needs to be 2, let's go ahead and balance the equation. Here's my acid. The acid reacts with the base to form a salt. Now, the salt will be the cation and the anion combined. Now, barium is +2, nitrate is -1. So barium nitrate is Ba parentheses NO3 close parentheses 2. And that's aqueous. This is the salt. Why do I have to have 2 nitrates? Because barium is +2 and nitrate is -1, and this is overall electrically neutral. Plus, remember, we're just swapping ionic partners. In an acid-base reaction, we swap ionic partners. The H plus combines with the OH minus. There's only 1 H plus here, but 2 OH minuses. That's why I need a coefficient of 2. And I will get 2 waters, which I'm going to write water a weird way. H, OH. And I write water that way just to emphasize that for every H plus, there must be an OH minus. So this is water. So in an acid-base neutralization reaction, they swap ionic partners. The acid reacts with the base to form a salt plus water. The mole-to-mole ratio here is not 1, and therefore we cannot use M1V1 equals M2V2. Let's write underneath here what we have. The concentration of nitric acid, or the volume, is 25.0 milliliters, and the concentration is 0.125 molar. For barium hydroxide, we're looking for the volume, so I'm going to put milliliters question mark. How many milliliters? And the concentration is 0.1 molar. Okay. Now, I'm going to put right here, important. I'll draw a line to separate this from our problem. And I'm going to say important. M1V1 equals M2V2 does not work here. And it does not work here because the mole-to-mole ratio is not 1 to 1, it's 2 to 1. So in this case, here's how I would go about doing this. Now this says what volume and molarity is normally in liters. We can calculate liters first and then convert it to milliliters. I'm going to do this like a dimensional analysis problem. I'm going to first of all write down what I want to know. I want to know the number of liters of barium hydroxide solution. The number of liters of barium hydroxide solution. And number two, I'm going to start with the given measured quantity. Now notice there's three numbers here. Which is the given measured quantity? Well, the important thing to see here is that molarity can be used as a conversion factor. So let me add that right here. This is another important statement. So important. Molarity can be used as a conversion factor. So I'll just put a little box around that. Molarity can be used as a conversion factor in dimensional analysis. So there are three numbers given here. Write down what you want to know. Number two, start with the given measured quantity. Why do I always emphasize the given measured quantity? Because you never start with a conversion factor. This is a conversion factor. This is a conversion factor. So the 25 milliliters is the given measured quantity. I'm going to go ahead and convert this to liters. I'm going to move the decimal place 2 places over, and this is 0.0250 liters. This is of nitric acid solution. So I need to get liters of HNO3 solution down here. I didn't write liters of nitric acid solution, but that's what it is. I converted 25 milliliters to liters. And what is my conversion factor? Well, it's molarity. Remember, anytime you see capital M, I think moles per liter, and I can even replace it with moles per liter. This is saying there's 0.125 moles of HNO3 per every liter of solution. That's what molarity is. It's at this stage that I'm using molarity as a conversion factor. This is molarity as a conversion factor. Okay, so that the liters of nitric acid solution cancel, and I have it in moles of nitric acid. I don't want it in nitric acid. I'm converting to barium hydroxide. So I need to wake up screaming mole to mole ratio. I put moles of HNO3 in the denominator and moles of barium hydroxide in the numerator. And the mole to mole ratio from the balanced equation, 1 mole of barium hydroxide, the coefficient is understood to be 1, reacts with 2 moles of nitric acid, so 1 to 2. Be sure you see where I get the mole to mole ratios from the balanced equation. So moles of nitric acid cancel, I get it in moles of barium hydroxide. I'll say times, draw a line, and I'll put moles of barium hydroxide in the denominator. Now, once again, I can use molarity here as a conversion factor. So here I'm going to use molarity as a conversion factor. So when I read that the concentration of barium hydroxide, or underneath here in green, is 0.1 capital M, whenever you see capital M, you can always think moles per liter. This is 0.1 moles of barium hydroxide per liter, or 0.1 moles of barium hydroxide per liter of barium hydroxide solution. So this will give us the number of liters of solution. The number of liters of solution, when I multiply through, everything in the numerator I multiply, everything in the denominator I divide. I ignore ones. Be sure you're doing this calculation so you're getting the right answer. And you get 0.0156 liters. And if I go ahead and convert it to milliliters, because we were given milliliters here, it's just more convenient to work with, move the decimal place 3 places to the right, and I have 15.6 milliliters of solution.